Hello everyone, today's topic about diode analysis. How a diode analyzes a circuit. So let's start first, ideal diode versus practical diode. That means definition of diode current and voltage of ideally and practically. So first, let's see example to explain ideal diode and practical. So first, what does ideal diode means? Ideal diode is a theoretical purpose for usage or calculation, etc. But practical diode is commercially available diode, you know. So as you see in this circuit or in this picture, we have a power source and also we have a diode and a resistor. So when our diode is replaced ideal diode, so first consider during reverse bias. During reverse bias, our RD diode of resistor, it becomes infinitive ohm. That is infinitive resistance. So that means during reversing biasing, a diode is reverse sort of our source. So that means when our positive battery connected to the cathode side and the anode side connected through a resistor back to the negative side of our battery. So during this time, that diode, it becomes open circuit. So a voltage through a resistor cannot be dropped. No voltage drops through our resistor. So our current becomes zero current. But in hence, through this diode, our voltage becomes the same as or absolutely equal to with our V source, that is our 10 volts. That we can call it, as you know in the previous, peak inverse voltage. So during reverse bias, it has a resistor diode becomes infinitive, means open circuit. So no voltage drops through resistance, the current becomes zero. That is impossible current in the resistor. But what happened during forward time? During forward time, our RD becomes zero. So that means let's show you our circuit when our source, the positive side of a battery connected to the anode side of a diode and the cathode with the resistance and the resistance of negative side of our battery. So during this time, the diode, it becomes as a conductor or as a switch. So the diode becomes closed. So during this time, a voltage drops through our resistor. So what about our current? So the current becomes, as you know, Ohm's law, V over R, then 10 volts over 1000 ohm, it becomes 10 milliampere. So during forward time, we can get a current. So as you remember during the characteristics of a diode, ideally a diode becomes zero voltage but high current during forward time. During reverse, less than zero voltage but no current. So this is a reverse bias during this time forward time. So during forward time, perfect conductor. During reverse perfect insulator, our diode. This is ideally definition of a diode. What about practical diode? Let's see practical diode. That during practical diode, that our diode, it may be used as a silicon diode or a germanium diode. That is a potential difference. That silicon diode is 0.7 and for germanium diode that is 0.3 is potential difference in the diode. So during that time, practically diode, let's assume our diode is silicon diode. So let's first consider reversing biasing. During reverse biasing, our diode is reverse for source. So the positive side of a battery connected to the cathode side and the other sides of the resistor to the negative side of our battery. So during this time, the diode block the voltage source. So that means the diode becomes open circuit, our diode. So no voltage drop again through a resistor. No voltage drop through a resistor. Now during this time, the current becomes 0 ampere or 0 milliampere. But some minority current we can get, as you know, is during characteristics of diode. During reversing biasing, when our V source is not exceeded that the range of reverse voltage, the current some minority voltage becomes here. But when exceeding the reverse voltage, that the diode becomes damaged. This is reversing practical diode. Some minority current becomes get, but not real current. But what happened during forward time? During forward time, the positive of our battery connects to the anode, the cathode side of the diode to the resistor, and back to the battery of negative side. So during this time, a voltage drop through our resistor. So what's the performance of our current? So the diode becomes conduct. So that diode, if you assume the diode is silicon diode, so the drop voltage of the diode is 0.7. So a voltage drop in the resistor becomes 9.3 because our source is 10 volt. That 0.7 drops through the diode. Then our current becomes 9.3 right over 1000. It becomes 0.9 or 0.09 amperes. So during that time, as you remember, our characteristics principle of a diode, something fine drop and our current becomes perfect. That's fine drop is our nil voltage, that is 0.7. So this is forward conduction. During this time is reverse conduction. So this is ideally versus practically diodes. If you have any questions or doubts, you can write in our comment sides. As you see in the previous about ideal versus practical diode analysis, now let's see load line analysis. The load line plots all possible combination of diode current and voltage for a given circuit. The maximum ID equal V over R and the maximum VD equal to V source. The point where the load line and the character curve intersect is the key point which identify ID and VD for particular diode in a given circuit. So when you see this circuit in figure 2.1, it's a simple circuit, and also in figure 2.1b the characteristics of diode. So let's see example to determine the load line analysis. First, determine by Kirchhoff's voltage law, solve the circuit. That means V source minus of VD minus of VR is equal to 0. So to find VD and ID, let's set VD equal to 0. Then when you get to ID becomes V source over R. When VD set to 0, that we can get maximum current. And let's set ID equal to 0. Then to find VD. So VD equal to a V source when ID becomes 0. So we can get maximum voltage. Then, as you know, the characteristics of the diode, that is our nil voltage 0.7, then plot the maximum current and the maximum voltage. When you plot it straightly, that combine the characters of the diode, that is the characteristics, and that is the plot load line. So this point, we can call it Q point. Q point. Q point means at this Q point, that the diode is practically operated. Then we can get IDQ, and also we can get VDQ. So by this method we can get the value of current, solve the resistor, and the value of voltage drop, solve a resistor. Let's see example. Our circuit 10 volts is our diode, and our resistor 500 ohm. This is silicon type of diode. 500 ohm. Okay. Now let's see analyze this circuit. Find first ID. ID becomes V over R. 10 over 500 ohm or 0.5 ohm. Calculate it. When you calculate this one, 10 divided to 500, it becomes 0.02. That means 20 milliampere. That is a maximum current. What about VD? VD equal to V source. that is 10 volts. Then plot the load line. This is not perfect, but assume as the example this is 20 milliampere. This is 10 volt. Then plot the maximum current and the maximum voltage. Then, as you know, the characteristics of a diode, that is 0.7, that is our key point. When the key point is moved to the horizontally, we can determine the IDQ. Let's say this one is 18.5 milliampere. 18.5. And also this voltage assumption is 0.78 volt. This assumption, but perfectly scaling our graph. Must perfectly. Then when you get IDQ and VDQ, then let's find VR. Then V source minus VD, this is our VD, don't forget, minus of VR, it becomes 0. Then VR equal to V source minus of VD, that means 10 minus 0.78. So VR becomes 9.22 volts. So the voltage through a resistor becomes 9.22. So what about diode resistance? RD. RD is equal to VDQ over IDQ. Then VDQ 0.78 over 18.5 milliampere. Let's calculate. 0.78 divided to 18.5 milliampere means 0. Let's calculate it. 42. It becomes 42.16. This is the resistance of a diode. Then we can get ID, we can get VR by that means to our circuit. Sorry. ID is equal to V source over RD plus R. That's the date. RD means resistance of the date. That's our circuit becomes, look it, like this one. Sorry, circuit. So this is RD, this is resistance. Then this becomes our V source 10 over 42.6 plus 500. This becomes what we get, 18.5 milliampere. We can the same. What about voltage through a resistor? That is voltage divider. We can get it also this one. So VR is equal to R over RD plus R times V source. Then R is 500 over 42.6 plus 500 times 10. Then we can get for this value 42.6 plus 500 plus 46 when times 10 is calculated 6 plus 542.6. So this result becomes 9.22 volts. That is a voltage through a diode. So the equivalent circuit for the operating condition only can be drawn as shown in the picture. So this is the load line analysis. But when you're working with load line analysis, must be perfect scaling of current diode and voltage diode. Then we can move horizontally or vertically. But the best one is we can use approximated method.